Good day, ladies and gentlemen, and you're all very welcome to today's technical session of the CNPS. My apologies if we're a little late in starting. I personally have had some teething problems with administrative facilities from StreamYard, and I've actually luckily got the help of David de Hilster, who's actually going to administer today, so he'll put me up and down when necessary. But I'm delighted to say that our two speakers, Dennis Allen and David Bauer, are here, and they're going to talk today on, well, there was a slight error actually in the announcement, because following on the earlier talk from the two gentlemen using Neo-Newtonian mechanics in electromagnetics, actually, the Neo-Newtonian mechanics was carried over to today's talk, but it's actually incorrect. It should be classical mechanics. Classical mechanics to produce a neutron model entailing mutual spin pumping, generating a very small amount of extra energy. And the further spiel is that to produce a neutron model entailing mutual spin pumping, generating a very small amount of extra energy, E, that is currently, and they say mistakenly, postulated to be a neutral neutrino, particle of mass E equals E over c squared. That's using E equals mc squared. So they're going to talk about that. You will notice that it's part one. So part two is scheduled to start. I think it'll be 4 weeks' time. We'll make the requisite announcement for that. So I hope we get over all the problems today. As usual, although I will have to enlist the help of David, who's kindly stepped in. I'm delighted that he has been here. What we'll do is we'll scan through the comments and the questions which has come in on the Facebook and YouTube, and we'll deal with those. But I'll have to refer to David with those as well, because I can't see them all as administrator. And similarly, there will be a private chat from people in the green room. Now, before I lost administrative facilities, I see that we have a number of people in the green room. So hopefully we'll bring them up for a fuller discussion. And I think our speakers today will be referring to this Alan Bergman model, which was published in Common Sense Science some time ago. Perhaps without further ado, I'll ask David. Now, there are two things. First of all, I have to bring up the slides because I have them here. I might actually send them to David and ask David to bring them up.
You should be able to share them, can't you?
Okay, I can share them as an ordinary. Of course, I should be able to. Okay. Well, so what I want to do, David, is I want to bring up the slides, and I want to bring David up as a speaker, or ask you.
That's fine. That's fine. That's fine.
So shall I bring up the slides now?
Yeah, go ahead and bring up the slides. Sure.
Mm-hmm. Okay.
Let's do that.
This is what I set the thing before I got rid of things. Now, all I have to do is get the slides up now. Can you see those?
No, we don't see anything yet. Yeah. So
Okay.
right now, people, we're just trying to get the slides up. Keep talking when you do stuff. Explain what's going on. That keep.
Yes, indeed. That's a very good advice. The slides are up in my system, but it takes a moment or two to get them. So I think presently you're all going to say you can see them. I hope you do anyway. Can you not?
Oh, yeah, I got it right here.
Okay. I was trying to maximize it a moment ago. I got it to the total part of the screen.
I forgot. But, I have to show it. We're good.
So that's all right, is it? Yeah, you probably have. No, you shouldn't have to do something, because I'm sharing my screen now, am I? But that's a problem for you if you want to bring David.
No, there's no problem. So let's go forward. We can bring
Okay.
them up. If you can watch the slides, you'll just be with them. There's no problem there. Okay.
Okay. And you'll have to
So
tell me when to advance because I can't see the total
yeah,
thing.
the speakers will ask you to advance. Does that sound good?
That's perfect. Yeah, that's
Okay.
perfect.
So I'll bring up David and
David, they said we'll talk to the slides.
okay.
Okay, I guess I'm on, right?
I can hear
Yeah.
you.
Yeah, my name is David Bauer. Dennis and I were involved giving a talk about, I think, a month ago on Neo-Newtonian mechanics. We talked a lot about gyroscopes, inertial mass, and so forth. Today, we're going to transition into the Bergman-Allen electron model. I want to explain my role in this research. I consider myself kind of like a graduate student trying to learn from my professor, Dennis P. Allen Jr. Not only am I a graduate student, I'm kind of a poor graduate student who probably is right on the borderline of being kicked out of the university due to my delinquency. I'm just trying to learn all that Dennis Allen has done in research. So the first slide, Bergman-Allen electron model, this all began, I think, about 6 months ago when I sent Dennis Allen a copy of Kowick's paper on, well, I reference it in the third slide here, electromagnetic moment and electron inertia in a current circuit. And in this paper, Kowick uses a rather typical model of an electron, a spherical model, but he gets results which are not in accord with experiment. At which point, Dennis Allen wrote back and said, would you like to get involved in trying to correct this model? And I said, yes. And that's where we are today. So anyway, in the second slide, I have, in my haste, I misspelled Bergman as Bergson. It should be the Bergman-Allen electron theory and its extension to neutrons and the electron-positron ether. It reminds me that Einstein once had two assistants working for him, Bergman and Bargman. So I imagine there was a lot of misinterpretation trying to get their names right. Here, the next slide gives some references that we'll be talking about. Of course, we have the classic book by Dennis Allen and Jeremy Dunning Davies on Neo-Newtonian mechanics. Then we have the article I just spoke about, written by Kowick back in 1955, actually before I was born. Then we had the article by Achilles on Back to a Tenable electron model. And then we have the three papers explaining the current model, no pun intended, the electron model by Bergman and Allen, Electron in the Ground Energy State, published in the Journal of Common Sense Science. Actually, the article has 3 parts, and I've listed the dates of publication, part 1 to part 3. So let's go to the slide saying point number 1. We cannot model the electron as a spinning spherical ball of charge, electric charge, as Kowick did in his monograph, which we briefly talked about in our last talk, because he quite honestly points out that such a model is unstable, and there's nothing to keep the charge from being extruded at the poles, because after all, this electric fluid is repelling itself. Each part is repelling the other parts. So think about the Earth's magnetic field and the Van Allen belts and the aurora borealis. You know, you have all these particles coming in towards the poles. The Earth's magnetic field simply cannot protect it from charged particles coming from the sun at the Earth's magnetic poles because the flux lines almost become perpendicular there. And also, to make E equals mc squared, we have to have a certain binding energy, which must be postulated to exist as well. And Poincaré was the one who added these Poincaré stresses to these different models of the electron. But as we'll see, as Dennis Allen has pointed out, we don't need these stresses because we can confine the electric fluid simply via its magnetic field. Okay, any discussion on point number 1? I think a spherical model for the electron is still an improvement on the point charge model for an electron. When you think about how infinitely small a point is, you wonder how could anyone think of an electron as being a point charge. Furthermore, that energy would have to be infinite at the origin. All right, let's go on to point number 2. So these two problems that we just discussed vanish if we use a spinning charge ring as an electron model instead. And actually, we're going to have the electric fluid will form a toroid. And in that case, you can get equilibrium purely from electrodynamical forces. The magnetic field will constrain the charge to circulate in this toroid. However, there are mathematical singularities in the charge density function, but we can handle these quite simply. Here, we note that we can distinguish physical singularities from mathematical ones. And so we actually have a physics theory which makes sense. It's not really a bunch of confusing gibberish, such as Einstein's general relativity, and which is disproved by Professor Dimitrov's experimental work, which refutes Einstein's equivalence principle. So again, the model, which was actually initiated by Bergman, is a toroid, and Dennis Allen came in to perfect the model, to perfect the mathematics. Any discussion on point number 2? Point number 3. So we're going to present this model as a toroid or torus containing spinning negative charge with a large radius r and a small radius little r. You understand the big R is the distance from the origin to the center of the toroid, and the small r would be the diameter of the circle, which is revolved around the z-axis to get the toroid. It also has a toroidal charge density symmetry and toroidal charge velocity symmetry as part of this model. Okay, Dennis, you have any comments? Somehow I can't hear Dennis Allen. Ian, is there any way that you can allow me to hear Dennis Allen? Ian, can you hear me?
I'm surprised David is not responding.
I'm here. I mean, but you have control. You're up there. Everybody's listening.
That's David. Yeah, there you are. Yes. So he's just asking David to put Denny up now to respond to something.
Yeah, I'm sorry. I had a phone call, so I wasn't planning to be here, so that was my fault.
Yeah, no, it's great that you're here. Thank you very much.
No problem. Who needs to be up there?
Denny, please.
Dennis Allen?
Oh, Dennis. I was looking for Denny.
Oh, sorry. Yeah. He called.
Can you hear me now?
Yes, I can.
Oh, I see. Okay. Well, yes. I see there's a remark. Now charge magically spins from James Keen. I would say to James that you do have to have some kind of a model for the electron. And the Coulomb's law just causes the positive or the negative charge, either one, to expand because like charges repel. So you have to have something to contain the charge. I chose, with David Bergman, I chose the Lorentz law of force, which causes the magnetic field around the ring, which compresses it and makes it in equilibrium. So you have to, but the Lorentz law of force has a velocity term. So you have to, if you're going to model this successfully, you have to have the charge at each point having a velocity, a well-defined velocity. So I understand James has his own model and he's pushing that, but I think he should, in all fairness, realize that if you're going to model using continuum mathematics rather than his model, which is discrete, you're going to have to allow each point of space to have a charge, whether it be zero or whatever, and also a velocity, or you'll never get the charge to be contained because of Coulomb's law. So he says more circular thinking. Yes, well, the charge is going around in a circle, isn't it? But we get some pretty good numbers from this, and I think James, if he continues to listen, will be impressed.
Okay, Dennis, I think at this point you were going to present your spreadsheet and your numerical calculations with some input from me.
Yes. Can you bring up, Ian, can you bring up the ground state, energy state SW draft 3?
Ian, can you hear us?
I can hear you, but I don't think you can hear me. Can you?
Yeah,
Well,
we can hear you.
I'm doing all this, but you can't hear me.
We can hear you.
We can hear you.
Oh, good. I didn't think you could. Okay. So is that the one you want, Danny?
There's nothing on the screen, Ian.
Nothing on the screen. It takes a moment.
Oh, there it is.
Here we are. Yeah.
There it is.
Well, it's. I was afraid of this. It's the type is so small; it's awfully hard to read.
Yeah, I could probably increase it some way. Here we are. There's a thing up there at the top. Is that better?
Yes.
Is that all right?
Yes, that's good. Thank you.
A little bit more, Ian.
A little bit more.
Phil,
Okay.
Yeah, get the text wall to wall on the sides. There, that's good. That's yeah, okay.
Well, I have
just
to shift it.
move it over. Just move it over a little bit.
Yeah, you can expand it, I think. You
There
can.
you go. There you go. There you go.
Yeah, go in a little bit, and you can expand it further.
You want more?
Every time you expand it, you'll have to recenter.
No, that's too much. Yeah, but it's too much. I'll have to go down again. That's as big as I can make it and fit
Okay,
everything in.
that's probably good.
Okay, well, first we have some notation, and the script E subscript, well, not subscript, EI is potential energy and indicates electrical energy, and script E sub O is potential energy. Subscript E indicates electrical energy, but outside the ring. And E sub SI is magnetic energy inside the ring, and E sub SO is magnetic energy outside the ring. So, in other words, what we do is we postulate a spinning charged ring. There is a boundary, but it's not rigid. All previous models of the electron have been basically spherical balls that were visualized as like billiard balls or something. There was a discontinuity at the surface. But we've adopted a different approach. Throughout all of space, we claim that we postulate that the electron pressure, the pressure at any point in space is a second is twice differentiable, continuously differentiable throughout all of space. So, in other words, the charged ring, as you approach it from the inside of the ring, as you approach the surface of the ring, it goes to zero at the boundary. But it goes gradually to zero. It goes twice continuously differentiably to zero at the boundary, so that there's no special cases. The thing is very smooth. The whole model is smooth throughout all of space. It turns out that there is a mathematical singularity. There are mathematical singularities, but they are not physical singularities, because when you consider the charge within a certain radius, that's twice continuously differentiable without any singularities. And that's very important, because if there are if we ignore this advice, then we find that there are a whole bunch of special cases. We have to treat what discontinuities in either the charge density or its time derivative, or its derivative as it moves along. Whereas if we assume throughout all space we have second derivative, continuous derivative existing, it avoids all these special cases that you might otherwise have to use. Now, we read in the various physical constants, and we hope to calculate the such things as the gyromagnetic ratio, which is anomalous for the electron, the magnetic moment, which is also anomalous. We hope to get definite numbers that are not anomalous. The problem is that, for example, take a Penning trap, which is used to measure the mass of an electron, which is about 9.11 times 10 to the minus 31
Kilograms.
kilograms. I lost my train of thought. The
Penning-
mass will equal the electric energy integrated throughout all space inside and outside the ring, divided by c squared. That will be the gravitational mass. And the inertial mass will be the magnetic energy integrated throughout all space, divided by c squared. And so the total energy we postulate as being mc squared, where m is the total mass, inertial plus gravitational, which are separate. And so the whole thing will largely revolve around the calculation of the energy throughout all space, both inside and outside the ring. Now, it's been noticed by many people that if you use a point particle as a model, you have an infinite amount of energy because the column forces become infinite. And so the Cowick, for example, moved to a sphere with a non-zero radius to avoid this problem. To avoid this problem, but then you have a discontinuity at the surface of the sphere, which leads to all sorts of special cases. Dave and I decided, mainly Dave, that we should instead have a smooth distribution of charge throughout all space, and such that as we move along, the time first and second derivatives as we move are also continuous. Now, let's see here. Now, there was three types of motion that we could see that the charge in the ring might take. One is it goes around the ring, and it would have to be at velocity c to make the math come out right. And then one which might be called twisting, in that as the charge goes around the ring, as you can see in the diagram here, the charge twists as well as spins around the ring. We were able to show, though, that this couldn't happen, that the twisting velocity was zero by using this diagram here on the screen. So that left just a spinning charge. And so we had to postulate a density function. The density outside the ring would be zero. The density inside the ring would be given by, let's see here. On page 9. Can we go to page 9? Okay, wait, I think you've gone by it. Let's see, what page is this? The 9 is in the upper right-hand corner. I don't see a 9 here, so I think you have to either go down or up. Yeah, outside electric potential energy. Yeah. We have a formula for that. The capacitance of the ring is given by this equation, 4 pi squared epsilon naught r, the large radius of the ring, over the logarithm of 8 capital R divided by lowercase r, where lowercase r is the small radius of the ring. And then we can compute the energy from the capacitance here. I don't know if you can see my cursor or not. Q squared log of 4 capital R over little r over 8 epsilon naught pi squared capital R. And so we were able to, can you scroll down a little bit? Yeah, that's the energy outside the ring. Now, if you scroll down a little bit more, we have to integrate, we have to give the charge density inside the ring a formula. The rho is the radius of if you take a cross section of the ring, the radius from the center to some point inside the ring. And as rho goes to little r, that lambda goes to 0, of course, because there's no charge at the ring surface. It's smoothly. Okay, so we did a 4-term Laurent series. The Laurent series has a singularity at the origin here. R, little r times res, the radius, RES, which is the residue, from Cauchy's integral theorem, and over rho, which is the radius. Unfortunately, we couldn't get Greek letter rho. We had to type in RHO. So the residue then is the value that determines the charge density near the center of if we take a cross section near the center. But it goes to infinity. However, there's a B0, a constant term, a B1 rho over R, which is the rho term, and then the B2 over R squared times rho squared, which is the rho squared term. However, when you go to integrate anything using a circle, you have to integrate not just a function, which would be lambda of rho here, but you also have to use a Jacobian. Now, the Jacobian of a circle, no, don't go any further down. Go the other way. The Jacobian is the radius. So when you multiply the radius times lambda, the singular term R res over rho times rho would be just R res. So the singularity of the Laurent series vanishes once you go to integrate using the Jacobian rho. So although there's a mathematical singularity here, there's no there's no actual singularity, no physical singularity. Now, this is unusual. Most of the time, if there's a mathematical singularity, it's assumed to be a physical singularity. That's because theoretical particle physics has become so mathematical in nature that it's no longer possible to distinguish between the physical singularities and the mathematical singularities. If you see a singularity, even though it may be just a mathematical singularity, it's assumed to be a physical singularity. And there's been a book written about all this, not two books that I hardly recommend. Let me just get them right now here. Sorry, I should have had this ready to go here. Okay, the first one is Lost in Math by Sabine Hassenfelder, Dr. Sabine Hassenfelder, a theoretical physicist, particle physicist, somehow connected with the accelerator at in Switzerland and France there. And it talks about how physics has become way too mathematical, and it's an interview of a famous physicist by her trying to get to the bottom of all this. It's very excellent book. I highly recommend it. The other book is The Higgs Fake by Alexander Unzecker, which is subtitled How Particle Physicists Fooled the Nobel Committee, by which she means fooled them into thinking that the Higgs boson had been discovered when actually he pointed out that it hadn't. Of course, this is completely and totally, it's way off the beaten path. Let me put it that way. But we introduced this Laurent series for the charge density and hoped for the best. I mean, we didn't know if it would work out or not, if we might come into a contradiction at some point and fail. But it turned out that it did work quite well. And the singularity here that you see goes away once you integrate it using a circle to integrate around, because of the Jacobian, which is rho, which you have to multiply times lambda. Okay. So we go about trying to calculate the coefficients, res, B0, B1, and B2, the four unknown coefficients, to see if we can do it without coming into a contradiction. Well, turns out we could. The first thing we note is that this function lambda when rho is equal to r, the small radius, the charge density goes to 0. And so lambda there at r, rho equals to little r, is 0. So we get a condition that B1 res is equal to, let's see, well, let me just, Well, if we turn to page 10 now, page 9, we get res is equal to minus B0 minus B1 minus B2 because it has to in order for lambda to go to 0 at rho equals r. So we get our first condition. We have 4 unknowns, and we have now one equation involving those 4 unknowns, which is res equals, can you see the cursor here, anybody?
Yeah,
Hello?
I'm looking for the cursor.
Yeah, res is equal to minus B0 minus B1 minus B2 is our first equation connecting the 4 unknown coefficients. So we're off. All right, now we talk about, if we scroll down a little bit, charge is a function of the radius rho. Okay, we know that the charge at the surface of the toroid, the charge within the surface of the toroid is equal to Q, the charge of the electron. Since it's an electron model, it has to be. So now we compute using this condition, and we get an equation for B0. And that is, B0 is given by 1, right here, 1/6 8 B1 plus minus 8B1 minus 8B2 minus 3Q over pi squared R squared capital R. And so we have another equation, and it turns out to be a quadratic, and hence has 2 solutions. Let's see here. We better go to the next page. Okay, we have to compute the various energies first. That's a little involved, but assuming we do that correctly, we go to page 12. And we notice that the spin angular momentum of the electron is equal to h bar over 2. After we compute the various energies, we set the spin angular momentum of the electron equal to m sub s, which is the mass of the spinning charged ring. It's the angular, we want to compute the angular momentum. So it's the mass times the linear velocity times the radius. That's a formula for spin angular momentum. And the spin angular momentum for an electron is h bar over 2, where h bar is Planck's constant over 2 pi. It's called Planck's rationalized constant. And So we don't only use the mass corresponding to the magnetic energy, not the mass corresponding to the electric energy, because magnetic energy is what goes into the spin angular momentum, not the electric mass energy, which I assume we've computed on the previously. So in other words, we're treating this in a sense, as a mechanical model. We're using the usual equation for the spin angular momentum, which is the mass times the radius times the linear velocity. And we know that from Planck's work has to equal, and Dirac's work, has to equal h over 2 pi, which is Planck's rationalized constant, also known as the Dirac constant, divided by 2. So we've used, we've got 2 solutions. One, however, involves a positive residue, that is, which would correspond to a positron or a proton. The other has a negative res, which corresponds to the negative electron, of course. So we know which solution to choose for B11, for B1. And so we're down now to 3 equations and 4 unknowns. So we've almost calculated everything, and we're hoping that we don't get a contradiction, because then we'll have to start over from scratch. Well, it turns out we don't get a contradiction. And we compute well, maybe I should say a little bit about the energy. This takes us back to page 1. Can we go back to page 1 here? Yeah, the rule of signs here. The electrostatic potential energy, charged segments of the same sign repel the 2 segments. And then we're quoting from Wikipedia here. The electrostatic potential energy is negative if the charged segments have opposite sign, and positive if the charged segments have the same sign. Since the spinning charge ring is composed of charged segments of the same sign, the 2 electric potential energies inside one and outside the other, integrated inside over the inside of the toroid, integrated outside of the toroid, have positive electrostatic potential energy. Positive mutual potential energy corresponds to repulsion between 2 charged segments, also Wikipedia. Now here we come to the magnetic potential energy. Charged segments moving in the same direction attract the 2 segments. It follows that magnetic potential energy is negative when the current elements have the same sign. Thus, the spinning charge inside the ring generates a magnetic field E sub SI, and one outside generates a potential energy E sub SO. They both have negative magnetostatic potential energy. All right, now, if the magnetic static potential energy is negative, then since we're dividing by c squared to get to mass, and c squared is positive, it's a square, we have then that the inertial mass, which is what corresponds to the magnetic energy, magnetic energy divided by c squared is equal to the inertial mass And the electric energy divided by c squared is equal to the gravitational mass. All right, so the magnetic potential energy, strictly speaking, we have to say that the inertial mass has to be negative. Now, Paul Dirac used negative inertial mass, and but in a much more complicated way, and it's hard to understand. Well, this is easy to understand because the reason it has a negative inertial mass is that it's a reactive force. It's not an active force. The inertia only becomes active when a force on an object, the inertial force of an object only becomes active when the force on the object is non-zero. If there's no force on an object, the inertial force vanishes. But if there's a force, the inertial mass pushes backward because it's a reactive force. Like friction is sort of a reactive force, except that friction only stops when motion stops. Whereas the inertial mass kicks off, stops when the applied force stops. So we take this inertial mass as being positive because it's too confusing to but we know that we can distinguish in our model between a reactive force and an active force. All right. Now, let's see, what do I want to do next here? Do you have a comment, David?
Nope.
Okay. So it turns out then that the gravitational mass is equal to the electrostatic energy integrated both outside the ring and inside the ring, and that's positive. And the gravitational mass, we have to divide by c squared, of course. And the gravitational mass is the magnetic energy integrated throughout all space divided by c squared. And we don't put a negative sign on it because, Newton used a positive sign and everyone knows his theory. But it actually does have a negative sign. And now I've lost my train of thought.
Can you explain why the inertial mass is the magnetic energy throughout all space divided by c squared, whereas the gravitational mass is the electrical energy? Where does that concept come from?
Well, it comes from a lot of places. Morton Spears had an article in Galilean electrodynamics where he had a capacitance model for gravity. He died, however, before he could finish up, and his loyal daughter, who is now a professor of economics at some large Western university, published his notes as best she could. I took those notes and finished it up and published my first book, Foundations of Neo-Spearsian Gravitational Theory, with application to earthquake early warning systems. I tied that in with
the name of the book again, please. Foundations
of Neo-Spearsian Gravitational Theory with application to earthquake early warning systems. So the first 4 chapters, there's 6 chapters in that book. The first 4 chapters are completing the Spearsian theory. The 5th one is some philosophy, and the 6th one is tying it in with earthquakes. Now, this is not just Morton Spear's weird idea. Mike Gamble, who was a former Boeing supervisor, told me a few years ago, I think a couple of years ago, that he was working on a device invented by a Russian inventor, which you could stand on it, and if you activated it, it would fly off. It would carry you off into space. And I never found out. At the time I was working on something else, I never followed it up on it, but that would too indicate, because this device was electrostatic in nature. And so apparently this also shows that gravitational mass is electrostatic in nature. Then there's a paper, The Action of an Electrostatic Potential on the Electron Mass. It turns out that if you put a electron in the middle of a charged sphere, the mass of the electron, which can be measured by the fact that it's part of a glow lamp, which glows the frequency of the globe depending on the mass of the electron. The mass of the electron can be shown to change as you change the charge on the sphere that contains the electron in the glow lamp. That's an electron-activated glow lamp. So this shows that if you separate the Earth, which is the ground, of course, from the electron by encasing it in a sphere surface of which is charged, you can alter the gravitational mass of the electron, up or down. I think I've sent you this article, Ian. Do you remember it?
You're talking about the article by Effect of the Electrostatic Potential on the Electron Mass?
Yeah.
Yeah, you sent that to me. I have a copy.
And I think I sent it to Ian too. Do you have that? It's
What's
not,
it called?
Unfortunately, it's just a number. The name of the slide is just some kind of a number. I thought you might remember it.
Yeah.
I do remember it. Yes, I do remember it.
Can you bring it up?
It's got a number on it. Yeah, it's not labeled.
A number. Well, then it must be in my emails then.
I sent you two in an email. I sent you two numbered slides, one of which was this.
Computer.
Well, maybe I can resend here. I have another computer here.
No, I have it here. All I do is I have to get my account
Okay.
up. Can you hear me now?
Yes.
Don't
Yes.
You can. Oh, you can. Okay.
Yep, we can hear you.
I'm sorry with this old computer. I once I get the mail up, I can get. You just had a number, you say.
Yeah.
Oh, it's a nuisance.
Let's see.
Wesley.
Well, let me just let's not waste too much time here. I see we're past the hour mark. It's the title of the article is "The Action of an Electrostatic Potential
Get this
on
all
the
sorted
Electron Mass."
up, set up on my new computer.
D.F. Mikhailov.
Can you download it from the internet?
I'm sure that would take longer. I mean, I have it in my emails, and it's taking me a few minutes to get into the emails. I have it here, actually, on the file, but I couldn't find it when you say it was just a number.
Don't you guys have it? The other two gentlemen, they could
I was looking at it just a while ago. If I can get it here.
I have it.
Why don't whoever else has it can share it? Anybody who has it can share it.
Well, I don't know how to share it from my computer.
There's a little button underneath that has share. It's a little computer with a plus sign on it on the bottom. Sorry, folks, we're just trying to load up something here. So what? So what are we loading up? Want somebody describe that while it's happening?
Okay, it's the article, "The Action of an Electrostatic Potential on the Electronic Mass," on the electron mass. Abstract: an experiment herewith described proves that the electron's mass is changed when it is placed anywhere inside a charged spherical shell at column potential capital U.
Here, let me see. Upload. I'm going to upload this file here. Here, I'm going to upload it. I think it says it's processing. Yeah, there it is. Action of electrostatic. See?
Oh yeah, good.
So
Good.
anyone can download that.
Enlarge it a little bit.
Let's see. Remove from stage, edit name, remove from studio.
You can't. What happens with those kinds? I don't think you can change it size. If you upload a file, it goes to their server, and you don't have control.
Can someone download that from what I just uploaded?
No. Yeah. They
Well,
can't. But go ahead. Let's go forward. So I mean, on my screen, and I've got it. I don't even have full screen.
They have a glow lamp, which is energized electrons emitting light or radiation anyway. I don't know. It must be light if it's a glow lamp. And the frequency of the light emitted depends on the electron mass. And you can get all sorts of frequencies by enclosing it anywhere within this charged sphere, because it cuts off the electron from the ground, which is the Earth. And it fools it, you might say, and makes it think that the ground is now the charge on the outside of the sphere.
Huh.
And so as a result, the frequency of light emitted changes as you change the electrostatic potential of the inside of the sphere, which contains these electrons, which are part of a glow lamp, which are glowing as the lamp sheds its light.
Huh. Interesting.
So, in other words, what he's doing is he's confusing because of the equivalence principle. Everyone thinks that the electrostatic and the gravitational, electric and the gravitational and the inertial mass are the same, or at least equal. That's the equivalence principle. But Alexander Dmitriev has shown that that's not true. Ron Hatch has shown that that's not true as well. And but they cling to it because it's the key to the equivalence principle. Is the key to Einstein's general theory of relativity. And so, if that's wrong, then Einstein's beloved curved space-time goes down in flames. Well, they aren't ready for that. So, and Roger Anderson talks a lot about this sort of thing when he's talking about special relativity. It also affects special relativity negatively as well, and that's even, if anything, it's even more beloved than the general relativity among the physics elite. So anyway, that's why the gravitational mass is electrostatic in nature, and the fact that the inertial mass is magnetic energy divided by c squared is given by the fact that, one, it's a reactive force, so we get a negative mass, and the other is that the inertial mass and the electromagnetic and the gravitational mass are the same for low velocities, usually, not always, but usually. Ron points out, however, that although for zero velocity, he took it pretty much to be the same. When you increase the velocity, the inertial mass goes off as according to the gamma factor, but the gravitational mass goes off according to a different factor. So there again, the equivalence principle, excuse me. So there again, the equivalence principle goes down in flames, but they don't want that. That's their favorite curved space-time. Wow, you know. So anyway, but there's no way to convince them. A man convinced against his will is of the same opinion still. But so anyway, David, does that?
Yeah, that helps.
Okay. I guess maybe we better ask for questions. It's I've talked for an hour, and we've both talked for an hour, and so now it's time for some questions, I think. Ian?
Well, can I ask a question?
Yeah.
Who's that?
This is David. Can I ask a question since
Yeah.
I'm still in the learning stage here?
Yeah.
So this toroid is symmetrical. Let's call it the z-axis. It's symmetrical about the z-axis.
Yes.
Okay. Which
Things are on the z-axis.
Symmetrical about the z-axis, which we could also say is a spin axis, right?
Yes.
All right. So this toroid is the charge. I guess it's like a charge current that's flowing around. Can we call it a charge current? I mean, a fluid, a charged fluid.
Yeah, it's a current. Yeah, it's a charge moving at a velocity.
It's a charged fluid, since it's continuous.
But it's not granular. It's not
right.
granular.
It's a fluid. All right, say a continuous fluid is circulating around this toroid. Now, if I were to cut it, include the z-axis, but cut along the xy plane, I would have two circles, right?
Yes.
I would have two circles. Now, if I look at those two circles, will I see the density of the charged fluid? It's obviously not uniform. It's 0 at the edges of the circles, right?
Yes.
The density is 0 at the edges of the circles, right?
Yes, that's right.
But now let's call the z-axis along the bottom, which goes through. I mean, not z-axis, but the x-axis. If I were to traverse the x-axis and go from the edge of the circle on the left to the inner circle on the left, and then the inner circle on the right to the outer circle on the right, would the density of the charge fluid, what kind of symmetry, what I'm trying to get is what kind of symmetry is there of the charge fluid inside these circles where I've cut?
Well, it turns out that the large radius is of order 10 to the minus 16, I believe, and meters. And the small radius is of order 10 to the minus 199 meters. So in other words, the small radius is incredibly near 0, but it's not actually 0, which is important because if it is 0, then you have an infinity, which you can't calculate anything from. So in other words, below we get the small radius being of order 1 over 10 to the 199 power, it's not 0, so we can calculate with it.
Right.
And yet it's close enough to 0 so that you can take it to be 0 for most practical purposes.
But what I'm saying, if you look at the cross section of this toroid,
Yeah,
let's just take this very, very, very small circle,
yeah,
and magnify it thousands and thousands and thousands of times, and look at the charge, the density of the charge current. And let's put an origin right in the middle of that circle.
yes.
What kind of symmetry do we see for this charge?
Circular
current?
symmetry.
Huh?
Circle symmetry.
Okay, so it's large in the middle and goes progressively to 0 at the edge.
Yeah, and it's a 4-term Laurent series. So the charge pressure is a 4-term Laurent series.
But I would think that there'd have to be some sort of influence of one circle on the other circle.
Yeah, there would be, but it's so small you can't even. I mean, it makes this 10 to the minus 199 power seem large. It's so small.
You understand what I'm asking, right?
Yeah, I do. You're saying that the part of the circle that's closest to the center of the ring should be affected more than the part of the circle that's on the opposite side.
Right, by the other circle.
Yeah, but the thing is that what you say is true, but the effect is so small that you can ignore it completely.
Yeah, because the circles are so small in the first place, it would have very little effect on the other circle.
So you can actually, the effect is completely and totally 0, except that it's not quite 0. And this explains, of course, why, they always say, well, we can't really have a point particle because then the energy would be infinite. But yet we're going to assume we do have a point particle because it works. Why does it work? Well, it works because it's not actually a point particle, but it's a ring whose large radius is about 10 to the minus 16th meter, and a small radius is about 10 to the minus 199 power. So if for all practical effects except that, at some point you want to compute the energy, and then, or the things like the gyromagnetic ratio or the magnetic moment or whatnot, you have to, you can't start from infinity and go anywhere. you have to have some kind of a number, no matter how small.
And with this model, you think that you can fix Kowick's?
Yeah, well, no, this model is only partial fix for Kowick. Kowick had three things that were wrong that I could find. One was he had a spherical model for the electron. Yes, we're fixing that. We have a spinning charged ring that doesn't explode. Then he had he threw out the what do you call it? He threw out the current drift. The current around a circuit drifts. The charges flowing in the opposite direction of the current drift at about 0.5 millimeter per second, very slow. He threw that out and announced that he was going to assume that the charge was moving, a very small portion of the charge was moving at velocity 1/20th the speed of light about, and the rest was not moving. And so he threw away the drifting current velocity, which can actually be measured indirectly. And there was one other thing that he had trouble with, I forget. I think that was because he assumed that the charge moved down the wire, straight wire, in a straight line, when it circles, it spirals down. So this Bergman-Allen model does fix the fact that he had to use a spherical model for the electron. It does, but the other two things that are separate.
Well, this is interesting because if I understand what you're saying correctly, the magnetic effect of a current is not due to the motion of spherical electrons per se. It's due to the alignment of the electron spins by the electric field. Is that kind of this Achilles excuse me, this Achilles model? You say that most physicists assume that it's the, can you see me? It's the motion of these electrons down a circuit which is generating a magnetic field. But we know that the electrons have a spin magnetic moment. You're saying that the electric field orients these spins, and that's what causes the magnetic field. And not only are they not going straight down, but they're spiraling.
Yeah.
Am I correct, Dennis? Is that what you're saying?
Yes.
Because a lot of physicists like Purcell was the one who thought of this or popularized it, is that the magnetic field is due to the electrons drifting down the wire and then being Lorentz contracted. You've heard this argument.
Yeah, I've seen that. Yeah.
But other physicists have disproved this idea that this is just ridiculous. They say that's not that can't possibly be true.
I wonder, could I just add a very basic?
Yeah, go ahead, Ian.
Just two things, Danny. One is, you've probably come across some of these ideas where the electron does not occur outside the nucleus. Say Ido Cal has this SAM, or standard atomic model or something, where the electron is actually situated within the nucleus. So I'm just wondering if your model would contradict that, or would you have any ideas on that? And also, with regard to the model, are there any experimental measurements done of distances or magnetic or electric fields which would indicate a preference of your model over the conventional point electron? I mean, you've given heuristic ideas, but are there any experimental details? So I have two questions there.
Well, there are experiments. There's, for example, the Penning trap, which measures the mass of the electron. Are you familiar with that?
Yeah, I know of it.
All right, so that they claim they can measure it to I don't know, 10 significant figures or something.
And are you maintaining that's more consistent with the Bergman-Allen model than the conventional model?
No, the Bergman-Allen model is independent of the mass of the electron. We just use the mass of an electron, but it works for any mass that's positive. That means, in particular, that if you took the data from the Penning trap experiment, you might find that although that data was fit pretty well statistically to the idea that the electron would have a certain mass, 9.11 and so on, times 10 to the minus 31 kilograms, that there might be, that just might be the mean of the distribution. There might be a small standard deviation as well. And if you check various small standard deviations and see how they made the Penning trap data fit the data, you might find that you got an even better fit from the idea that the electron is not just one mass. It's like a bell-shaped distribution with the mean being 9.11 times 10 to the minus 31, but the standard deviation being non-zero. You might get an even better.
You might. I mean, has this been done, Denny?
No, this would be not that anybody knows about, because this was just totally anathema to the standard model. The standard model says, let me quote here. Dave quotes from a book on page 16, I think. Yeah. The value of the electron mass is given as a fundamental physical constant by Kodat of 2006. Evans assumes that rest mass is an invariant property of the electron. Here's a quotation from Evans, The Atomic Nucleus, page 177, 1955. We assume throughout that if a neutron, proton, electron, neutrino, or meson enters the nucleus, the particle retains its identity and extranuclear characteristics of spin, statistics, magnetic moment, and rest mass. But the SCR model, that's our model, explains that the electron mass changes if the electron is accelerated, binds to one or more other charged particles, or is energized to an excited energy state. First, consider the state of a free electron that remains in the ground state when some ionized molecule comes close enough to bind to the electron to the molecule. At out 97 and out 98, our model shows that the electron radius r is not forever fixed, but depends on one variable, the ground state mass energy u. In contrast, the Copenhagen atomists assert that the properties of an electron do not change but remain fixed when a ground state electron enters into a molecule where it can remain bound to other particles that constitute the molecule. If the electron rest mass and mass energy always remain constant, then the atomic weights of the elements would be predicted from the sum weights of the constituent particles. However, the mass energy of the neutron is considerably greater than the combined mass energy of one proton and one electron. Atomists account for this extra neutron mass energy by adding various particles to the neutron. But the common sense science accounts for the extra neutron mass energy by the mutual energy that links one proton and one electron together in one atom known as the neutron. Our out 100 is our model's prediction of the relationship between the mass energy of the electron and its size, thus providing a physical mechanism for exchanging and storing electromagnetic energy among multiple charged particles. The SCR particle, our model, conforms to the law of conservation of energy. Second, for the case of the electron in an exciting energy state, to be considered in another paper on electrons on excited energy states, radius r, or its equivalent of the loop length in a helical structure, could be a variable that provides the mechanism for the radiation frequencies or spectral lines that are observed in discrete wavelengths, such as predicted by the Rydberg equation.
Dennis, what were you quoting from there?
Page 16.
Oh, of the spreadsheet here?
Yeah.
What about the position of the electron or the location of it, whether it be outside the nucleus or not?
We haven't gotten that far yet, but Bill Lucas has his model, which is very similar, where he finds that there are no neutrons inside an atom in the nucleus or elsewhere. They're all just protons and electrons.
Yeah, that's the same as Lido Cal's theory, as I understand it.
He does this by calculating the masses of all the various isotopes, every last one, radioactive or not. And then he and his son Joe actually do this. And so they calculate with enough accuracy so they can show that just electrons and protons constitute the atom. And where the electrons are inside the atom delineates the structure, I guess you could say. I sent you a book, what is it? The Universal Force by Bill Lucas.
Oh yes, which I read. Yes.
Yeah, remember that? He had pictures of neon, helium, stuff like that, and how the electrons and protons were distributed. Remember those pictures?
I do, yes, I do.
Now, Dennis, let me ask a question here. This spinning charge ring would act somewhat like a gyroscope.
Yes.
And so is there any evidence of nutation and precession of these electrons?
Nutation and precession involve one end of the turning thing being tethered more tightly than the other end.
Right.
And otherwise it just spins.
Right. You're right. Yep.
Okay. I think Green Science has put in a few claims. I don't know if he used AI in the first instance, but he's claiming that various experiments have shown that Mikhailov and the other experiments were not correct. So I'm just wondering if we could put up a couple of those comments. I don't know if David's still around. But
I'm here.
No. I mean, David Hill.
you
I've no control. You must think I'm pretty effete now. I just have no control at the moment. There he is. Yeah, he's in. So, do you know how we can hover over some of these comments, David, and put it up?
Which one? Which one are you wanting?
Well, Green Science started by saying in the comments 2021 study, a team by Martin Tadgmar published a definitive test in 2021. They used an electron beam and spherically to 20 kilovolts and looked for a charge in the electron trajectory. He then goes on, he says they didn't find this. I don't know if you can see that. It's a little bit up.
No, that's not.
Yeah, well, that's where it starts. That's where I think he used AI.
This one? This one?
Yeah. Yes. And then he goes on. He continues, says, for a change in the electron's trajectory due to an altered mass, is the very next one. They found no variation within their experimental accuracy, ruling out the predicted effect by 2 orders of magnitude. Are you familiar with their
No, I
experiment?
haven't heard about that. But that, the Mikhailov thing is only one experiment. We've got Mike Gamble's work. We've got various other.
I think Wesley is very sympathetic to it. I think there was some debate whether the factor of 3 in the denominator was correct or something. I think we might have looked at that in the past, but I think he's very sympathetic with this view. In fact, he accepts it, I would say.
Well, Wesley and Dave Bergman, I think it was, before our model came along, created a model where all the charge was on the surface of the toroid. And he got some results there.
Right. See, this green science puts another example in, Birkhausen-Kurtz oscillations, and he said they didn't find the correct things. I don't know. Yeah.
Well,
I mean, one could a bit impishly say that this sounds a bit like mainstream trying to defend. He gives another one here, the Tolman-Stewart experiment. So benchmark here demonstrate that the carriers of electric current in metals have the same mass to charge ratio as free electrons. Contradicting the idea that an electron's mass can be arbitrarily changed by its electromagnetic environment.
well, if you want to read Bill Lucas's Universal Force, he seems to refute that. He and his son Joe computed the mass of every single atom, including the various isotopes, radioactive or not. To using the theory, they could predict the exact to I think 8 or 10 significant figures. So their data has to be considered here, I think.
Well, we might refer green science to Bill Lucas's The Universal
the
Force.
Universal Force.
Is it part one? Was that?
The Universal Force, Volume 1.
Yeah, quite so.
On Amazon.com.
Yeah, Amazon.com. The last comment is the mass of the entire system goes up. Alan's claim is very different. He is asserting that intrinsic inertial mass of one component particle within that system can be altered by an external field. Well, again, have a look at those diagrams.
Well, now, before he said the mass stayed the same. Now he's saying it goes up.
Yeah.
What is going on here?
I'm not sure. Unfortunately, we can't put him up. But I'm wondering, David and gentlemen, if anybody in the green room wants to come in. I think Jim Keane has made a number of statements, maybe critical statements. Would he like to come in, or somebody else, or even invite?
He's not here.
Is he not here? Oh, he's gone. Okay. And yeah, okay. I don't know if Vladimir is there or he was in initially.
Yeah,
Vladimir
we're the ones left in the green room right now.
Oh, okay. We've bored them off. Okay. Right. Well,
I'd like to say that, and he says the mass of the whole system goes up in that comment. But the system is made out of electrons and protons, and electrons and protons all have the same behavior under the, as far as the mass going up or down.
Dennis, I have a question.
Yeah.
This is David Bauer here. So how did you said you wanted to make some comments about the electron positron ether? How would your model relate to the electron positron ether of David Toom?
Yeah, he's got a very interesting electron positron ether, but he has to assume that the reason that the electron and the positron don't unite and explode, one being positive charge, the other being negative, is that they revolve around each other at a high rate of about their center of mass at about a high rate of velocity. However, that may not be true. If you use the spinning charge model for the electron and the positron, it may be that you don't have to assume this high rotational rate. One has to calculate to find out for sure, of course, but it may be that this particular part of his model, which sort of, everything's spinning and so on, needn't be the case if you use this particular model.
Something just clicked in my mind. There's a lot of articles in, say, like the American Journal of Physics that talk about the vortex model of magnetism and vortex model of this and that. So it might be able to relate your work to this vortex model. Do you know what I'm talking about, Ian? The vortex sponge, etc.
Yes. Sorry, I was just looking at some of the comments there. You're asking David how it relates to that, are you?
No, I'm just saying it might. There might be some connection between this work of the toroidal electron model to the vortex.
Well,
sponge.
the vortex model assumes that when you have an inflowing vortex, the ether is going off into God knows where. And where you have the outflowing vortex, it's coming from God knows where. That's the whole problem with the model.
So you don't like the vortex model of the ether?
Well, it's a magical model. Here, all of a sudden, things are appearing in the outflowing vortex, and they're disappearing in the inverting.
Well, it's no more magical than the Big Bang Theory. I mean,
Well, yeah, but I don't go with the Big Bang Theory either.
Yes. Right.
now let me ask a practical question. As someone who wants to actually reproduce these calculations and possibly improve them or take them to another area, if I wanted to obtain Mathematica, can anyone give me any guidance about that? There's licenses and subscriptions and all this kind of stuff. What's the cheapest, best way to obtain Mathematica? Does anyone know? If not, we'll just skip this question.
Well, Danny would have the most experience in that. I mean, you've used that and you've used Derive.
No, it was Dave Bergman who used it, and he used the dues he got from Common Sense Science to pay for it.
Oh, I see. So it's pricey, probably, to buy a license.
But I had a friend who was a professor. I think he's dead now, but he was a professor at Michigan Tech where I used to teach. And he said that he got, after I left, he got Mathematica for free for being a professor emeritus.
I used Mathematica as a graduate student, but that was years ago.
Well, you may be able to get yourself hired somewhere as an adjunct professor. Really?
Okay.
That's what David did. I think David is an adjunct professor. David, is that true?
Yeah. It's not easy to get to have that happen. I was a little bit lucky, but yeah, you can. So I don't know about Mathematica because I haven't heard really of anybody I know who's actually been using it lately. So I don't even know what the price is. Certainly don't use large language models.
That's an advice, is it?
Well, for anybody who wants to know, use it now because the prices are going to skyrocket. Right now, we have it for our university has Claude, and it's already throttling. Basically, if you have a $200 script subscription now per month to use Claude, the actual burn rate of how much it costs from them to do it is in the thousands, if not $10,000 a month. So what's happening with the companies who are using large language models, which of course are probability machines, are never going to be, there's no logic there. They're useful, is that they're going to be so expensive that the smaller companies that are using them are probably going to drop it. I know my supercomputing group, where I retired, spent 2 years trying to evaluate Copilot, and after 2 years, they're not even certain that it's actually helping, because when you write code with a computer program, you got to go back and check it, and if it's wrong, you end up going down a rabbit hole. So it's interesting, because I'm in that arena. I had a book just published this week on a whole different technology, completely different from this. But if you are using large language models and you have it kind of open and you want to use it for big stuff, do it now, because in the next 2 months it's going to be throttled and become very, very expensive. So just my advice from an expert.
Well, Mathematica doesn't have anything to do with AI, I don't believe.
No, Mathematica is one of the really great tools around that's been there. It's all logic based. It's logic programming. All this, what they call AI as trained systems. I don't even call it AI. I call it artificial ignorance, but it's just basically trained systems. And you can't use trained systems in people are now doing agents, and they're handing over their computers to these agents, like, oh, you can now access my file system. And they wake up the next day, somebody did, and they thought, one of the agents said, oh, this folder is a virus, I'll get rid of it. So like I said, if you have real busy work that it can help with, do it now, because it's going to be out of reach soon, or poof. But yeah, Mathematica, I don't know. I haven't heard about that, but I know all these things are not cheap.
How much is your manual that you just published?
How much is the book?
Yeah.
Textbook, 25 years ago, my friend and I invented a computer programming language that allows programmers to capture what humans' knowledge that's needed when they read and do a specific task. This isn't like ask something. It's $50. It's $30 because it's 400 pages. It's a textbook for teaching the language NLP++. So that's what it is. We're hoping to start teaching that around the world. We're going to start in India and go there. But it basically allows programmers to take text and write real code, not train it, and be able to read and understand text and then do something with it. Right now, they're poking the village idiot, which I call large language models village idiot, trying to poke it to get structured data out of it, and that just doesn't happen. So what we've done is to invent a computer programming language that allows us to write, for instance, programs that if you were to have an app on your phone that was an assistant, it would actually understand every word and its meaning, and it would be written in a logical way with linguistic knowledge of that. So it's a 10-year project where it's going to take a long time. AI is hard. Real AI is hard. The reason they're training systems and you hear all this stuff is because they're trying to get tons of money. But it's a bubble that will burst. We're just not certain will, but we think it's coming soon.
I tried to use AI. It was someone who was using open access AI, chat bot or something like that. And I would ask it how to compute the moment of inertia of a certain mechanical device. Every time I asked it, it gave me a different answer, and every time the answer was wrong.
Okay, but no offense, but we are stupid to ask questions of a technology that can never answer that. What it does, it just looks at all the words that you put in there, and it's like a village idiot. It's listened to mathematics talk. It's listened to computer program talk, and then it just probability comes out with something, and it can be useful. But it would be the same way for you to type in your phone how many R's in strawberries and then wait for the autocomplete to give you the answer. It's not going to. There's zero logic there. It's just a dead neural net that's been trained on text in a clever way that has become useful. It's a predictive thing. Even its explanations are mimicking explanations.
David,
yeah.
I'm sorry, what is the name of your book?
If you go to book.visualtext.org, book.visualtext.org. It'll take you to the publisher.
Book.visualtext.org.
Org, yeah. But you know, maybe one I may just come on one Saturday and talk about the realities of AI. I mean, it is phenomenally a mess. Sam Altman, if you ever want, just go to Sam Altman and say problems with Sam Altman. This guy is one of the most shady characters on the planet. And you know, he's walking around with the president, and well, there's another shady character, but maybe I'll do that just so people, because I see people doing that all the time.
Because David, apart from the general interest, obviously, in the subject, it is very pertinent to natural philosophy, because in recent times, many of our presenters here have been using AI, and the discussions are using AI. So I'd like you to come in and maybe give an
That's
overview.
a good one. That's what I'll do. What I'll do is I'll put together a talk and talk about that. For instance, I'll give you some examples. Probability. If you just here's the way I look at when someone asks me, because I have been in NLP, which is large language models, is in that arena, and AI since the early 1980s. And I have seen everything that's come by. So when a person who knows that I've been in there asks me, a regular person, what's a large language model? I said, this is what a large language model is. It's the village idiot. He stands in the middle of the village and he listens to every conversation that goes on, everything. And after a while, he can talk like a realtor. He can talk like a mathematician. He can talk like a philosopher. If I follow a philosopher around long enough and I have no idea what he's saying, I can say what he says. A good example is there have been cases of people who have done that, who follow doctors around like interns, and then afterwards gone around and literally attended patients because they could mimic what was being said. And then prompting those is like trying to poke a village idiot to get him to do what you would like it to do. It doesn't make errors. It will never get better. In fact, they've reached the limit. You can only get so much probability out of text. It's looking at literally characters. It doesn't have any idea of what's going on there. So when people are asking about it, it's solved a few mathematical problems that have never been solved, but that's just because it's got so much mathematical stuff. The probability machine went in the right direction for that. And so, you know, it's like saying, I've got a random number generator on my phone, and it happened to hit 27. I went to the roulette wheel and it hit 27. Oh, it knows what it will stumble upon things, but you can't use it. And then there's a whole nother side of it, which is it's dumbing us down. I mean, I have students and they can write their entire project with Claude. Now, what's happening is, are you learning anything, or you're literally outsourcing your thought? And it dumbs us down. I've used it, and I felt myself doing that too. I just kept prompting. I don't want to do it. I don't want to have to write the program for it. I've used it for programming certain things. I've used it to write a book of 158 pages on expansion technology on NLP Foundation. So yeah, the number one thing is it's going to get really expensive. Number two, we don't even know if it's going to survive. Because the idea is this idea that it's like the internet before, the internet.com crash. Well, only a few companies got it and they're going to make it better. Large language models have reached their limit. And what's really interesting, Ian, is that one of the seminal papers that show this, which they don't talk about, is from physicists. Physicists have a seminal paper out there saying, look, we've taken every probability we can out of text, actually characters, not even words. And if you go beyond that, that machine will get worse. In fact, Claude, which is used across the world right now, it's the most used from Anthropic. IBM in January said, everybody start using it. In April, they made a report saying it's getting worse. The reason it's getting worse is so many people are using it, they don't allow you all that time in the brain, so your answers get worse. And they're going to start charging per token. And it can run literally, they are calculating, a company could be spending $10 million paying for tokens for a machine for something that's a probability map, you can never guarantee what's coming out of it is a truth or not. So the hype you get are people are wanting to scare us. It's going to take our jobs. All of you who are listening, it will not. It's not intelligent. It's zero intelligence. There's a lot of good people out there fighting the fight like this. But what's going to happen is the biggest thing that's going to happen is those people are paying $10 a month for Copilot. It's going to go up per token. Next thing they'll know is they'll have, oh, here's your $10. You get this much token. So you go and have Copilot do some, large language model stuff. And it goes halfway through. It goes, you're out of your tokens. $10 of tokens with one query. I mean, this is the reality. And eventually people aren't going to. People are going to use it. It's too expensive. And then, of course, the cost of taking. Well, there's the other thing is there's $1 billion in lawsuits right now. It has trained on illegal data. It's trained on HIPAA data. That's a federal offense. There's a young man who was part of OpenAI in California, and he was found dead in his apartment with 2 bullets in his head, one being shot in his bathroom, the other in his living room, and they said it was suicide. Sam Altman was asked about that. That seems really strange. Boy, was he nervous about that. What we think is that he was testifying against OpenAI for training on data illegally, and he was ready to testify. They came into his house trying to get his disk. I think he was there. Goodbye. His parents have been fighting for a year to get an answer because they have scared. The power of these people is enormous. It's ridiculous. But the good thing is they're running out of time, space, money. So, but that's a whole different
Well, I think
story.
we have an appointment, and we're quite convinced now of the relevance of it to what we're talking about.
No, I think I've told everything. So that's it. I don't have any more to say. So.
Do you have a name for your book, or is it just?
Yeah, it's called. Well, I mean, this is for programmers, right? What we did is we invented the dream programming language for natural language processing. If you are a programmer, you're not a linguist, you're not a computational linguist. You don't do those things. You don't know about dictionaries, knowledge bases, rule systems. And so what we did in 25 years ago, my best friend, he got a couple $1 million, and we invented the most, the only programming language ever invented for natural language processing. We launched it at the .com crash. You can imagine how that went over like a lead balloon. And then now people are starting to pay attention to it. So I think that's why in fact, a publisher came to us, and they're the largest publisher in all of Asia for IT books. So it's going to be a slow turtle. It's not going to be like it's going to take over. I believe all kinds of good things are things that go slow. If OpenAI and all that stuff had 100 million users in less than a month, it's going to fall just as fast. Because when people start getting, using it, and they use it for 5 minutes, and they go, oh, you want to use it some more? You've used 1,000 tokens. And if you want another 100, it's going to cost you $500. So anyways, that's what that programming book is for.
What is the name though? What is the title?
NLP plus, NLP plus, it's rule-based NLP using NLP plus plus. Rule-based NLP using NLP plus plus. Now, of course, it's not a toolkit. It's an empty language. You gotta program. So you can't grab it and start doing stuff. Although we do give you a parser in English and that kind of stuff. So it's really meant.
I have a grandson who graduated from college as a computer programmer. He can't get a job. I was thinking maybe I'd give him your manual as a present.
Yeah, you can. I mean, it is something we're trying to teach it, but it's hard right now. It's hard for computer programmers right now.
This guy is smart. He's just he has a personality which is the exact opposite of the hard sell personality.
Yeah, a lot of people. I mean, I think at times I'm autistic. There's a lot of people who seem kind of autistic who are in the computer science. So,
well, perhaps we should, David, give Dennis and David a minute or two just to summarize what they said today. And in the light, I see that we've perhaps started a discussion, about the relevance of the increase in mass and so on, and that might be something we can come back to. But if you'd like to summarize, gentlemen, and then I'll maybe just try to finish off insofar as I can, make a few pointers to David.
Go ahead, David.
Do you want to say something, Danny?
Go ahead, David.
Let me just say something for 1 minute. This whole project began about a year ago when I sent Dennis Allen a paper written by Kowick, who said that we should be able to see the effects of electron current,
That's David,
kinetic
yes.
energy. Yeah, this is David Bauer here. Kowick said that we should be able to see the effects of the kinetic energy manifested by electron current. Maxwell assumed that such kinetic energy and such momentum existed, but it was so small that it would have no discernible effect because experiments at that time were not able to detect it. But since then, they have been able to detect this current kinetic energy. So we are trying to explain using these different models, this model that Dennis Allen and David Bergman developed. We're trying to explain how you can calculate this electron kinetic energy and observe it actually. And that's my summary here.
Oh, okay. Is that sufficient for the moment, or do you want to add anything, Danny, before we close up?
Well, I think that if we pursue this, it will give a way out of the standard model, which is hundreds of particles and everything. Every time they can't balance out the energies, they postulate a particle. But David de Hilster has pointed out that, for example, for the neutrinos, as you go deeper into the Earth, the detectors detect less and less neutrino hits. And this shouldn't be, because neutrinos should sail right through the Earth, almost all of them. So it gets away from the standard model, and now they have besides quantum mechanics, they have wave mechanics, where particles are actually a bunch of different waves located at a certain point. They're not really particles. But we have, at a certain point, we have a vibrator, which is the spinning charge ring, which can vibrate in various different modes. And so they have all the vibrations that they're trying to guess from data. Well, we have the vibrator, which, given a good electromagnetic theory, we should be able to determine what vibrations occur and what don't, and how strong they are, and so on.
Okay. Well, I think you've certainly convinced us that this is a workable model, and to boot, it's avoiding this particle zoo, if you like, where, as you say yourself, Denny, they're postulating particles bilio as soon as they find that there's an imbalance in the energy and so on. And I think we've started a discussion about this whole question of the change in mass and related to Wesley's ideas and so on. And of course, as I said earlier, you're going to give part 2 of this in 4 weeks' time. So we look forward to that. I do apologize for the breakup today of the admin facility. And, it was very fortuitous that we had David there just to come in at the last moment. But it's a bit unsatisfactory where we don't have a control system. I had no control over what I was doing. But anyway, at least I was happy that I was able to project the documents you sent me. But the one document I couldn't find, the one we just talked about, the mass change, I probably had on my other computer because I had 2 computers. So I don't want to give you excuses, but I'm on an old computer here, which was linked up to admin, which I've lost now because I was trying to clear out the memory, and David and I will sort that out, no doubt. So thank you so much, gentlemen. You've gone to great trouble in giving us the last talk some weeks ago, and now you're giving us 2 parts of this very considerable work. And I know David has been asking a lot of questions as well, because he's been brought into this, and obviously he's found something in it, and he's given his own expertise. And the same can be said about Denny, because he got this Bergman model, and he saw some merit in it. And then he's gone into great mathematical detail, which we saw today as he went through the document with all those complex functions and so on. So thank you all very, very much. I hope we haven't frightened too many people away. I think some people in the green room may be left a bit early. Maybe they had other things. Maybe the weather's too good now. I don't know. But yeah, thank you. Thanks for a great presentation. That's come from David. So thank you all very, very much. And please forgive me. I hope everything will be sorted out by the next time. So David, we can probably end the meeting. And if you'd like to have a brief chat with me for a minute or two, that would be great. So I don't know if,
okay, sounds good. I'll take us out, and then we'll stop the stream. Okay.
Yeah, quite.